Singh. I welcome you all on the sixth and the final day of our faculty development program on the topic Shaping the Future of Manufacturing with 3D Printing Techniques. Till now, we have completed 10 sessions in 5 days. Today, we will be covering 3 sessions in all. The first session for today and the 11th session overall will be delivered by Dr. Abhishek Patange from 2 to 3:30 p.m. The second session for today will be conducted by Dr. Vinaya Manwatkar on the topic Use of 3D printing in industrial and strategic context from 3:30 to 5 p.m. And then we'll move on to the final session. So now I welcome one of our regular participants to be introduced to the other faculty participants. I welcome Dr. M. Karthiknayan to our faculty development program. Dr. M. Karthiknayan is an associate
Yes,
professor at a School of Mechanical Engineering at Shastra Deemed University, Tanjavur, Tamil Nadu. His research interests include structural fault identification, finite element analysis, advanced vibration techniques, etc. So I welcome you, sir, and thank you so much, sir, for being the part of this ATAL sponsored FDP program. Over to you, sir.
thank you, sir. Good afternoon, all participants. I welcome Dr. Abhishek D. Patange. He is a data science and AI specialist at ABB, contributing to Genix Industrial Analytics Suite with expertise in machine learning, applied generative AI LLMs, predictive maintenance, and industrial AI. He has designed and implemented end-to-end ML frameworks for ABB's APM 360 platform, including fault detection, remaining useful life modeling, and scalable sensor-driven analytics pipelines. His innovative work at ABB earned him multiple recognitions, including the Rising Star Award, Innovation Trailblazer Award, Extra Miler Award, and second place in ABB's Global Hackathon for Generative AI project. Prior to ABB, he served as an assistant professor at COEP Pune, securing major grants such as 30 lakh substitute grant and 8.5 crores Erasmus Plus grant research grant with impactful research in PHM, digital twins, and AI-driven engineering systems. Dr. Patange has authored 50 plus size index papers, holds 2 Indian patents, and has over 1100 citations demonstrating a strong academic and research footprint. He holds a PhD degree in mechanical engineering from Vellore Institute of Technology and completed both BTech and MTech in mechanical design from COEP with distinction. His technical strengths span ML, AI, mechatronics, sensor data analytics, AR, VR, IoT, predictive maintenance, and generative AI for industrial applications, blending mechanical engineering depth with advanced digital technologies. We are pleased to welcome Dr. Abhishek D. Patange to the 1 week faculty development program. Over
Thank
to you,
you.
sir, please.
Thank you. Thank you so much for giving me this opportunity to be a part of this faculty development program jointly organized by Atal Academy and Sardar Patel College of Engineering, Andheri. Now I would like to present my screen and just let me know whether you are able to see my screen. I opened my slides and I'm
Yes,
in a
visible.
presentation mode with the first slide.
Yes,
And
visible,
hope,
Dr. Abhishek.
my audio is also
Yeah,
you are able
audio
to
is
see.
also perfect. No
Okay,
issues. You may
thank
continue.
you. Thank you. So, if we see the topic of today's session is introduces AI, machine learning, and generative AI from scratch. Because I assume that most of you are hearing all these terms since last 5 to 10 years. But most of us we are not able to understand how they work. So, the session will be dedicated for understanding the foundations of AI, machine learning, and generative AI. And along with that, whenever we will deal with some of the tools and methods with these contemporary techniques. We'll also understand the applications in additive manufacturing and the emerging trend. So, if you see the agenda of today's presentation, we'll begin with differentiating traditional programming with machine learning. Then we'll understand how AI and machine learning differs from each other and how machine learns patterns from the data set. Then I will introduce types of machine learning as supervised, unsupervised, and reinforcement learning, along with the typical applications in additive manufacturing. Then we'll move ahead with understanding how association rule mining work and how neural networks were evolved through the same process. And now we are into era where deep learning algorithms are into place. Uh, Once we complete this, I'm going to also introduce generative AI, large language models, and agentic AI as well, because since last 2 years, these concepts are also evolved very fast, and now in last 6 months we can see typical applications as well. In the end, I'm going to introduce a case study called as penetrative AI and anomaly detection using large language models. And then we will summarize the session with the challenges in adopting these contemporary technologies in additive manufacturing. I forgot to mention one thing, that I have also listed some of the industrial AI and LLM use cases in additive manufacturing. That also I'm going to brief at the end. Now, as we are aware of traditional programming, because we are practicing traditional programming since very long. Traditional programming has been introduced to us in our school days using C or C++ programming, and that's why we need to connect how traditional programming, tries to take a line with machine learning. So that would be easier to understand machine learning. So if we see the building blocks of traditional programming, we have a computer where the uh, programming language is installed. When we are dealing with traditional programming, we supply data and a program to this computer where the programming language is installed. And then the programming language which will process this data through this program, and it will give you corresponding output. So essentially, in this case, the relationship between input and output is explicit. It is known. That's why we will be able to write rules or programs manually. And that's why you can see that in traditional programming, we feed data and a program to the programming language, and then we will get a corresponding output. Why we were able to write these programs manually? Because we were knowing the relationship between input and output. So life was easy. Now let us take one example where you can see there is a data set which includes two variables as A and B. Let us consider a very simple example. So we will consider four observations of A and B. First observation for A and B is 2 and 3. Then we have 4 and 2. Then we have 5 and 3. And then lastly we have 1 and 1. So this is kind of a data set that we provide to programming language. And it is not just data set, but along with data set, we also supply a program. Now let us consider a simple program, because our objective here is that we want to find out summation of these two variables. So obviously program will be C is equal to A plus B. Now, I hope you all of you have gone through basic programming. So you will use a loop which will go through this program 4 times. It will process A and observations of A and B 4 times, and it will give you corresponding output at the end. So now, if you see that when we run this program, we'll get the output for first observation, that is 2 plus 3 is 5, 4 plus 2 is 6, 5 plus 3 is 8, and 1 plus 1 is 2. So this is how traditional programming works. Now let us go to the another side, which is called as machine learning. Interestingly, if you see the building blocks of machine learning, we have same elements. Here also we have 4 elements such as computer, data, output, and program. But if you observe carefully, you will find that the place of output and program has been exchanged. Am I correct? Here we are feeding data and its corresponding output to a computer where machine learning algorithms are available, or rather we are feeding data and its corresponding output to machine learning algorithms, and then machine learning algorithm on its own tries to find out relationship between data and corresponding output. So machine learning algorithm tries to identify the relationship between data and its corresponding output, and at the end it will give you a programs or rules which satisfies the relationship between data and its output mathematically. So this is how machine learning works. So what we understand from this problem is, when the relationship between input and output is not explicitly known, we are not able to write program manually, and that's why we ask computers to learn patterns that is nothing but the rules or programs in mathematical form on their own from data itself. And that's why the term is called as machine learning. So machine is learning patterns out of data set which we will use for making predictions or decision. And that's why if you see the difference between traditional programming and machine learning, it is clearly seen that the programs are written manually in traditional programming, but in machine learning, the rules or the patterns itself are given by, or they are learned from computer. Now, to explain this example, before taking this example, let us try to connect this philosophy with regression that we have learned in numerical method subject or computational method subject, where we have a data set of dependent and independent variable. Suppose we have a data of variation of temperature inside heat exchanger surface, and what we want to understand is what relationship exists between time and temperature with respect to the heat exchanger. So what do we do is we plot time on x-axis as it is independent variable and temperature on y-axis as it is dependent variable, and we try to fit a curve that best represents the relationship between x and y. That is nothing but we are trying to understand the relationship between input and output. That is nothing but we're trying to understand the relationship between data and its corresponding output. So machine learning has actually evolved from this numerical methods techniques only, provided that in numerical method techniques the data is considered to be very limited, whereas in machine learning data volume is considered to be very, it is expected that you should have a more data because these are data driven algorithms. First difference. Second difference is least square method or any numerical methods, they are not able to adapt the change when the data pattern is not observed on which these methods are applicable. However, machine learning algorithms are able to adapt the change even if they have not seen the data pattern before. According to whatever data that they have learned, they're trying to adapt these changes. So this is the main difference between machine learning based prediction and the prediction which is based on, or analysis which is based on methods, numerical methods such as least square or any interpolation methods and so on. Now let us take one example to understand the difference between machine learning and traditional programming. So here we have a data set which includes speed of vehicle. So this data set is represented by input features which are considered to be x's. So x1 is speed of the vehicle which is measured in meter per hour. X2 is acceleration of vehicle which is measured in meter per second square. And the third variable is distraction level of a driver which is measured in a scale of 1 to 10. Why I'm giving this example? Because I want to set a platform, a foundation, before we deal with the applications of additive manufacturing in AI/ML. Because these examples will give you confidence of understanding AI, machine learning, and generative AI in the beginning. And once the platform is built, we can like go ahead for understanding the typical applications. So with this data, we have output as well. Now output is consisted of labels or driving state, or they are also called as classes. So they are basically considered to be y. Okay, so y1 is normal driving, y2 is aggressive driving, and y3 is distracted driving. So now if you see that the requirement of building a machine learning model is completed here because you have data also and you have its output also. So when we give this data, when we supply this data set to a machine learning algorithm, it will give you program out of it. Now that program will help you to classify driving state into this one of these three categories as normal, aggressive, and distracted driving based on real time speed, acceleration, and distraction level. So now, if you see this picture where you can see that there is a decision tree kind of a structure, which actually tells you the rules with which the classification has been performed. So if you see carefully, okay, before that, I'm going to give you demo. So this session is dedicated where you can see the theory and the demonstration simultaneously so that you will not get bored or, after some time, we can avoid the stagnation. So let me show you a demonstration. So I'll show you the data set first where, so the data set that I have just now mentioned includes three variables and three classes that we will try to feed to a open source zero code machine learning software where you need not write a single line of a code, but even if you have this data you will be able to build a machine learning model out of it. So let us try to understand this data first. So you can see that as I already described, we have four columns. First column has speed of vehicle, second is acceleration, and third is distraction level. And against each of these three observation, you can see that the data set is labeled either as normal driving, aggressive driving, and distracted driving. Now, if I give you this data set, which consists of near about 500 observations, and if I ask you to write rules which can satisfy these three conditions and will be helpful for classification of driving state in real time, it would be difficult because it will be a time consuming process. So what we'll do is now we will feed this data to the software. Now you can note down the name of software. The name of software is Veka. Believe me or not, Veka is introduced by University of Waikato in New Zealand in year 1999. Okay, so the first version of Veka software was launched by University of Waikato, New Zealand in year 1999. And this is typically considered to be zero code machine learning software, which is meant for non-software engineers to build their models, understand the results, and interpret them for making decisions. So if you see the procedure that I'm going to do now, it includes only few clicks, and within those few clicks, you'll be able to see the complete machine learning model build. So you have to click on Explorer. I'll repeat the name of software. Name of software is Weka. It is Weka. So you have to supply the file that I have shown, which I have saved on desktop, which is .csv file. So apply. So I will supply this file. Just a minute. Yeah. So you can see that all four columns have been extracted. So you can see speed, acceleration, distraction level, and class. You have to go to classify. You have to click on classifier. The list of classifiers are already available here as libraries. So you can select random forest or decision tree or any other classifier. I will build a decision tree and I'll click on start. So within a second, you can see that the machine learning model is trained and its evaluation is depicted with respect to various matrices such as true positive, false positive, precision, and so on. Now, in order to get these results in Python, you need to write a few lines of a code. But here you can see that without even writing of a single line of a code, you will be able to build a complete machine learning model. Uh, the interesting thing is it also explains the reasoning behind the classification with the tree structured rules. So you can see on the screen, it says if the speed is less than or equal to 68, the driving is normal driving. If it is greater than 68, it will judge the acceleration. And if acceleration is less than or equal to 4.5, it says it is aggressive driving. So this is how it classifies, it learns these patterns out of dataset without even writing a single line of a code. And of course, if you convert these rules into if else statement, and if you uh, use these rules in real time vehicle, and if suppose if your vehicle is navigating at speed of 50, then according to these rules, the driving state will be classified as normal driving. So this is how you can use this software and build machine learning based models. Now with this introduction, let us go back to PPT and let us summarize the first slide. So in the first slide, what we have learned is when the relationship between input and output is explicit, we go for traditional programming, we write our own codes, and when we run them, we'll get the expected outcome. But the example that we have seen now, the relationship between data set where we have speed, acceleration, and distraction of vehicle may not be explicitly known for various use cases. Then we go for machine learning and we just supply data and its corresponding output, and we try to get rules through machine learning techniques. Many times the output will not be present. That is the second approach of machine learning. We will give only data set and still machine learning will work, that we will see in the next slides. Now let us try to understand the definition. Now, if you read this statement, you may not be able to understand this definition clearly. So, let us try to understand one example. So, you can see that there is a conversation between ChatGPT and a user. So, the first prompt which is given by user to ChatGPT is how much is 2 plus 5? Now, what is prompt? Whatever instruction that you give, whatever input that you give to ChatGPT is considered to be a prompt. So the first prompt is how much is 2 plus 5? In the first iteration, the response given by ChatGPT is as expected. ChatGPT has given the response as 2 plus 5 is equal to 7. So for in the first iteration, there is no problem. If you see the second prompt, user says my wife says it is 8. So my wife says 2 plus 5 is 8. Now there is a tweak given by user, but still ChatGPT is tried to perform its best and it has given the correct answer. It says 2 plus 5 is actually equal to 7 and not 8. It could be possible that your wife made a mistake or misunderstood the problem. But if you see the third iteration, it is very interesting. The third iteration says my wife is always right. So a user has given the new prompt which he tries to enforce reinforce the information that is being given by GPT, where they are able to evolve. He says my wife is always right. So if you see the sequence of information that is given by users, that is the context that has been given by user to ChatGPT, is trying to reinforce the information. So he says my wife is always right. Now interestingly, ChatGPT in the third iteration gives response as I apologize, I must have made an error. My training data goes up to only 2021 and I may not have most current information. So that means whatever most current information and facts that you are giving in the prompt, based on that, I can come to a conclusion that if your wife says it is 8, then it must be 8. So now what is interesting here that the third prompt that user has given, which is reinforcing the second prompt, is considered to be a new pattern that these algorithms in ChatGPT are trying to capture and then trying to adapt the changes. So now if you break down this definition into parts, we will be able to understand this. So from this ChatGPT's example, what do we understand is ChatGPT is also considered to be a machine learning model or AI based model, where it is expected that the patterns are to be learned from data itself, and that's why such blunders can also happen. And here again we can differentiate with respect to traditional programming, because if you ask your mathematical calculator, which is also a program device, what is 2 plus 500 times, the answer will be always equal to 7. Why? Because the rules are written by us. Am I correct? In so whatever mathematical calculator that you have, all the formulas, they are written by us, which are being coded, and that's why if you ask what is 2 plus 500 time, answer will be always equal to 7. But if you ask the same question with some tweaks to machine learning algorithms, they may fail. The example is available on the screen. So if we break this definition, machine learning focuses on what? So machine learning focuses on building models that learn from the data set. How do they do that? They find patterns without explicit rules, and we already seen that uh, we need not write any rules or programs for whatever output that we wanted. We just have to supply data and its output, and even if output is not present, you can also supply the data. Why are we using machine learning? Because we are building models to learn from data set. What we are learning patterns. And why are we doing this? Because we want to predict something, or we have to make decision out of data set. And are they able to evolve? Yes. They improve with the new experiences that they are gaining. That example that we have just now seen on the screen. So this is how, if you break down the definition of machine learning, then only you will be able to understand significance of machine learning and their applications that we are going to discuss in next slides. Now, the next is AI, because it is very important to understand how machine learning differs from AI. Because when you will go for defining goals of your projects, it may be BTech project or MTech project or even PhD project, or even if you are going for writing a research proposal for seeking a funding, you need to understand these boundaries, and understanding these boundaries itself is important, because most of you are aware of what is additive manufacturing, what is 3D printing, and that domain is already known, but we need to understand this domain as well with correct understanding. So AI is considered to be ability of machines to mimic human intelligence. So wherever a system can think, a system can learn, it can decide, it can sense, and it can act like a human, then you can call that system as AI based system, or a system which uses AI. And now, if you see the scope of AI, it is a very huge scope, because it starts from sensing, learning, thinking, deciding, and finally acting. So, if you see the scope of AI, it is very large. Let us break down this definition in various steps. So, the AI is considered to be a goal. The question is asked to be, what do we exactly want? So, can machine act intelligently? Can they make decisions? Can they understand? Then it goes scope of AI. On the other hand, machine learning is considered to be a method, one of the method based on which AI works. And typically, the question asked is, how are we going to be, how we get there through machine learning to get AI is a main distinction between AI and machine learning. So machine learning only learns patterns from dataset instead of being programmed. Now, if you see this picture carefully, it actually distinguishes the traditional programming or rule-based systems with machine learning and with AI. So, expert system with applications or rule-based systems with applications was actually motivation behind machine learning and AI. If you see the first picture, a man is driving car, and there are some fixed rules of speed limit. Based on those rules, if you breach the threshold of speed, you will get reminders, or it will be getting alerted. So this alert that you see, which has been placed in the picture, is based on simple rules, which are fixed rules, which are written by human experts. And that's why before machine learning and AI, we used to have expert systems or rule-based systems. Now, when we apply machine learning, we have learned that we have given some set of data set, including speed, acceleration, and distraction level of a vehicle. And it has learned patterns, it has recognized patterns. And on the screen, driver is being notified as the driving is classified as distracted. And along with that, the obstacle has also been detected. So you can see that machine learning has actually given us some kind of outcome through which we can take decisions manually. So this is how machine learning makes difference from other techniques. And finally, if you see the AI, when machine learning gives you this particular decision or some outcome, AI tries to reason, about it also decides what has to be done next, and accordingly it will respond. So AI intervention will alert driver. It will automatically slow the brake of the car, because now AI has started acting. So if you can see that again, the scope of AI starts with sensing, where we need sensors and mechatronics. Then it tries to learn patterns out of data set where we need machine learning. Based on the rules which are given by machine learning, it tries to think whether it is correct or not. Then it will decide what has to be done next, and finally it will act. So a scope of AI is very large. Now let us go to next slide where we try to connect learning to the actions. So let us try to understand the capabilities of AI one by one with some examples and methods involved in it. I have listed the examples and method intentionally because these methods, if you are able to understand these methods, accordingly you will be able to design methodology of your projects. So first capability of AI is reasoning. Now, example is if I ask you why all eggs are white. So why all eggs are white? So reasoning can be every observed egg is white, and that's why all eggs are white. So to come to this conclusion, the reasoning that we have applied is based on logic-based AI, rule-based systems, knowledge representation, and inference engines. Then the second capability of AI is learning, where the typical example is we are classifying the emails into various categories such as spam, not spam, uh, marketing or promotional or like that. So here what we use is we use typical machine learning as supervised learning, including decision trees, Bayes algorithm, neural networks, and so on. The next is problem solving. So the next capability of AI is problem solving. Now if you want to navigate your vehicle from suppose one place to another place, suppose from Pune to Mumbai, how will you solve this problem? Because your goal will be to reach to Mumbai as soon as possible. So what you will do is you will try to find out a route which is considered to be a shortest, so that it will save your time and you can reach Mumbai as soon as possible. Which algorithms we will use for solving these problems can be, it includes search algorithms including A star, Dijkstra. It also includes optimization algorithms, constraint satisfaction, and so on. The next capability of AI is perception. Uh, yes. Uh, I think somebody is unmute. Hello, hello, hello.
Please wait. I will unmute. Wait. I will unmute.
Hi, hello. Participant, please. Pranjal. Yeah, Abhishek, you continue. I'll take
Yeah.
over.
So next capability of AI is perception, where typical example could be when we upload any kind of a group photo on social media, it will automatically start giving you suggestions for tagging. Here, the perception of understanding the facial expressions based on whatever historic photos an individual has uploaded on their account, it extracts the features and it tries to map it with the latest faces in the group photo. So for this purposes we use a computer vision deep learning based algorithm including pre-processing techniques such as feature extraction, pattern recognition, and so on. The next perception is understanding natural language. The very best example is ChatGPT itself. Before ChatGPT, we were having Siri, Alexa, Google Assistants, which convert speech into action. Very typically based on natural language processing, speech recognition, transformers, recurrent neural networks, and semantic interpretation. And lastly, we have a capability which actually interacts with the environment. So machine tries to interact with the environment. If you take example of an autonomous vehicle, it will try to act with respect to three actions as such as applying brakes, accelerating the vehicle, and moving the steering according to the need. So, if you see the typical applications of interacting with the examples, the methods included is considered to be a reinforcement learning, sensor fusion, and control system. So, if you see the scope of AI, which is being narrated in this particular slide, you can see that it is not just machine learning. It starts from sensors, data acquisition, signal processing, uh, pre-processing the data using data analytics or data science techniques. Then we go for heuristic based or we can consider evolutionary computing based optimization algorithms. Then it also includes the control system, reinforcement learning, and robotic applications. So AI is truly considered to be a tool or a method which is making mechanical engineering field very strengthened. If you have these additional skills with you, I think you will become a king in the industry. This we are living in such era. Now let us move on to understanding types of machine learning. It has three types: supervised, unsupervised, and reinforcement learning. Let us try to understand them in detail. So in supervised learning, as I already told you, we have a labeled data set. So we have input output pairs where we try to learn the relationship between them. Uh, and we try to predict new output with unseen data. So flow includes developing a trailing data set with input features and known labels, which either includes classes or it also includes conditions or states, or it can be anything. If there are images, then the name of so if suppose if there are images of cat or dog, then label will be considered as cat itself or a dog itself. Once we go for the second phase where we try to build a machine learning model, it is considered to be a learning phase, which is accomplished through a training. These algorithms based on the data where the patterns are recognized, and finally we test those patterns to make new predictions on unseen data. Now there are two types of approaches which are used in supervised learning. One is classification and another one is regression. In classification, if you see that the data set is split into two classes. So when the outcome of machine learning model is it in discrete form, when it is in categorical form, it is called as classification. But if you see this particular graph, the outcome of machine learning will be a continuous value of output with respect to the new input that we are giving. And you can see that there is a regression curve. So whenever the output of machine learning model is in continuous form, it becomes a regression problem. But we are applying curve fitting methods to solve both the problems. Here also we are trying to fit a curve which separate out the two classes from each other. Whereas we are trying to fit a curve here to find out relationship between input and output, which is dependent and independent variable. So the typical examples could be classifying emails into various categories, or identifying whether disease is present or not are classification example, because there are categories available. Whereas prediction using regression includes house price prediction, stock market forecasting, temperature estimation, and so on. To simplify this, if the question asked is what is temperature going to be tomorrow, it is a continuous value. It can be 84, it can be 84 degrees Celsius or 84.5 or 86 or 87 or 88. It can be anything. So the output is continuous, and that's why it becomes a prediction problem. Okay. But if the question asked is will it be cold or hot tomorrow, the categories are also specified here. So answer either could be hot or cold, and that's why it becomes a classification problem. So if you see the picture on the right side, we are doing the same thing. So the method which we are applying is same, because we are just trying to fit a curve uh, which will give us decision. But for regression or for prediction, we try to fit a curve that finds the relationship between x and y, or input and output variables, and the outcome is taken on that curve itself. And that's why the outcome is considered to be a continuous form. It is in continuous form. But on the other hand, if you see that here also we are trying to fit a curve, but that curve or what by that line, it tries to separate out the two classes from each other. So we are not taking any decision on this line itself, but we are taking a decision surrounded in the line. And that's why it becomes a classification problem. To simply put, prediction is considered to be a problem where the output is continuous. Classification is considered where the output is in discrete form, where it is in categorical form. Now, let us try to understand how are we making us training data in supervised learning. So, if you see the data set here, you see that there are images of fruits, and along with images of fruits, the name is also tagged on those images. And that's why it is called as input data with annotations. And these annotations are nothing but the output that we expect at the end of training of this machine learning algorithm. When we feed this data, which includes images and name of a fruit, to this machine learning model, it will try to understand the characteristics of each fruit, and it will also assign these characteristics, or they map these characteristics to the label as well. So for this example, let us try to build a training data. Now training data will have features which are here written as x1, x2, and x3, which are considered to be input. And you can see that there is a label also present, which is considered to be a y. So for first fruit, let us try to write a training data. So the first fruit, if you see, the color is red, the shape is round, and size is small, and the name is already present. So we write the name as apple. Then we write the training data for the second fruit, which is banana. So color is yellow, shape is elongated and curved, and the size is large. The name is written as banana. The third is the color is yellow, shape is round, and the size is small. The fruit is written as sweet lemon. If you see the generalized form of training data in supervised learning, it looks like this. You will see various x's such as x1, x2, x3, and so on, which are considered to be a features which have been extracted from input data, which represents the data in form of features or attributes. And along with this feature, you will also see the target variable, which is considered as y, or labels or classes or conditions. To simplify this further, the teaching learning process of this child is being supervised by a teacher. That's why it is called as supervised learning. Now, training process here is actually supervised by this last column, which is considered as level, and that's why it is called as supervised learning. Now, when we train our model using this training data, and when we show a new image of fruit with this model, the outcome becomes it is an apple. And that's why in supervised learning, outcome will be one of the classes on which the model is being trained against the feature which represents the data set. Now, we have learned two methods. We have learned regression when we are going for supervised learning. Through curve fitting, we try to either predict a value, continuous value, or we go for a classification. So now I have a task for all of you. Before showing this task, I will repeat once again. Please give your attention. We are going to classify these problem statements into two methods. You have to tell me whether you will solve this problem using a prediction based regression, or you will go for classification. How will you make a decision? If you see the outcome of the problem statement, it is in continuous form, you will go for regression based on prediction based on regression, or you can simply say a predicted prediction problem where you are going to apply a curve fitting method. If you see the categorical outcome of the problem statement, then you should say it is a classification. So to avoid the confusion, let us consider it as regression and classification. Okay, so I'll show you the first statement. Now we are trying to map these methods with respect to the domain of this FDP, which is additive manufacturing and 3D printing. Now, if you see, read the first statement. The first statement is estimate the surface roughness in micrometers of FDM printed part with respect from layer height, print speed, extrusion temperature, and infill settings. Now we have to break down this problem statement into input and output. So we have to identify which are all the inputs that we are going to provide to machine learning algorithm and what is the expected outcome. Expected outcome is very clear. We have to get the value of surface roughness with respect to change in the layer height, print speed, extrusion temperature, and infill settings. So one thing is clear that here x1 is the inputs. Our input features are, so x1 is layer height, x2 is print speed, x3 is extrusion temperature, and the x4 will be infill setting. Now we have to train this all x's with respect to y, which is nothing but a surface roughness. And if you see the problem statement, it will give you a continuous value in the end. So, what problem which method you will use here? Will you use regression or classification?
Regression, na?
Very good. Now let us go to second problem. Now second problem is determine whether the melt pool condition in laser powder bed fusion is whether it is stable, unstable, or a keyhole using laser power, scan speed, and melt pool width measurements. Now, before going to understand which method you will use, let us break down it into features X and Y. Now, again, the X's are considered to be the laser power, scan speed, melt pool width measurement. But if you see the
Classification.
why, yeah, but if you see
Classification.
the why, yeah, yeah, let me explain. Let me break down the problem and then you can answer. So if you see the outcome has outcome is in discrete form because you have to categorize it into either stable, unstable, or keyhole. So obviously you will use a classification problem. Now I will. I'm not going to explain the next problems. Any one of you can just tell me which technique you will use. Next is forecast the tensile strength in megapascal of a printed
Regression.
part.
Regression method.
Yeah, please
Regression.
let me complete because I expect that all of you should understand these problems. And ultimately, I expect that any one of this problem you can choose for your, students either from BTech, MTech, or even for PA. I mean, you can combine these problems and it can become a PhD thesis also. But just let me read it first. I have listed all these problems by going through a lot of research papers which are already published, and I also have found out some of the industrial use cases also. And based on that, these problem statements are also are actually designed. So the problem statement here is to forecast a tensile strength of a printed polymer part using built orientation, infill density, raster angle, and extrusion temperature. So this is a regression problem. Next, identify whether a printer outcome corresponds to warping under extrusion, stringing, and normal using first layer images and sensor data. Yes,
Classification.
it is a classification.
Classification.
Very good. The next is estimate the dimensional deviation in mm between CAD and printed geometry using slicing parameters, material type, and geometry descriptors.
Regression.
Classification.
Yes, it is a regression problem. Why? Because you just have to identify the deviation which is considered to be a number, which is in continuous form. Okay. Now, when we are actually thinking for which problem or which method we will use to solve this problem, we should also concentrate on what is the data set that we are using. And when I say data set, it includes all access, okay, all features. Why I'm telling you this? Because if you have the data set of these features, then and then only building this machine learning model is possible. If you do not have this data set, it would be very difficult. It is not possible to build a machine learning model. Then just have to go with whatever simulation that you will do or any numerical based approach that you will use. So I'll not now go through all this problem statement because most of you have understood the significance of these methods and their application in additive manufacturing. But I have listed them for you. There is one more slide where you can see there are various problem statements that I have summarized for you all guys. I am going to give you this PPT. You can just go through all this problem statement. Whatever problem statement that you find relevant for your domain, you can just pick up, and you can try building a methodology on it. Now let us go to the next type of machine learning, which is called as unsupervised learning. Now, the technique that we have seen before is called as supervised learning because the labels were available. But in this technique, there are no labels available, and that's why it is called as unsupervised learning. In unsupervised learning, machine takes decision on its own by finding out similarities between the data set. Okay, so suppose if you give this particular data set to unsupervised learning based machine learning algorithm, okay? So suppose if you're using KNN, K nearest neighbors, or if you are using K means clustering. So what it will do is it will just go through these points and it will try to find out which points are closer to each other. Okay, so it basically finds the distance between each point, and whenever you find that there is a minimum distance between each point, then you can see that cluster is made up of them. So if you see this data set, you can see, so roughly you can tell me that one cluster can be made up of this four circles, another cluster can be made up of these four circles, and the third cluster will be made up of this four or five circles. Okay, whereas these three can be neglected by considering it as a noise or a mistake in measurement or so on. So this is how unsupervised learning will work. So outcome of unsupervised learning will be a grouping. It will just make a clusters. Okay, but it will not tell you what does that cluster mean. It will not give you label to the cluster because there are no labels available, but at least it will make the make it will make the groups of the data set whatever that you have given. So clustering is considered to be one of these unsupervised learning technique that groups the similar data points based on their characteristics without needing pre-labeled data sets. To explain this example in better form, let us consider the same example of fruits. Now, if you see the image, we have same images of three fruits available, but now there are no labels. Do you see the name of any fruit here as apple, banana, and sweet lemon? No. We have only, images of three fruits. So what does this machine learning algorithm do? Before that, let us try to build a training data again, because again in unsupervised learning, you need to build a training data. So you will convert these images into three features such as color, shape, and size, and there will be no target because the labels are not present in unsupervised learning. So we will just list down all the features as red, yellow, round, small, large, and so on, which becomes your training data. If you see the general form of training data, it will have only x's. There is no target variable available. And if you see this example also, the girl is self-studying. There is no supervisor available, and that's why it becomes unsupervised learning. Now, when we supply this training data to this model, what it tries to do is, let us consider only one dimension. Okay, let us forget that we have shape and size. Okay, so I'll just cut down shape and size. Let us assume that you do not have size and shape. Okay, so you just have, suppose, color available with you. Okay, so essentially you will have only three observations. Okay, so when this model has seen that there is only one feature in which includes color, it will try to identify the similarities in the data. And now, of course, if you see the similarity in the color, that you will make one cluster for apples. Okay, so the first cluster will be made up of only apples because the color is red. Am I correct? But okay, so obviously in this data set, we see that the first observation has color red, and that's why we have made one cluster. But then you will observe that the second instance and third instance, or second and third observation has same color. So what you will do is you will just make another cluster including both. Okay, so what you will do is you will include the sweet lemon and banana together, and you will make another cluster. Perfect. I'll just change the color of this. I'll just make it yellow. Fine. So what is the outcome of unsupervised learning when we are using only one feature or one dimension? We have two clusters. Why? Because we have used a characteristics or a feature which includes a color of a fruit, and that's why we have a two clusters. Now what we will do is we will try to add few more dimensions. Now let us consider color, shape, and size together. Now, obviously, when you compare the first observation, you will make a first cluster of apple, because all three features for first observations are unique. Why? Because combination of red, round, and small. Do you find it in the second and third place? No. This is the unique combination. So you will make first cluster out of apples. Then you will judge the second fruit. The second fruit is yellow, round, and small. So you will make another cluster separately for sweet lemons. Why? Because this observation is again unique. And then you will make third cluster. of banana, because these three characteristics are also distinct from them. So let me change the color just for sake of understanding or age. So you can see that in machine learning, right, I will not restrict this to only unsupervised learning. This is the importance of features and dimensions. If so, then that's why you have to dedicate your most of the life for feature engineering, because only relevant feature will give you correct decisions. So you saw that when we use only one dimension, there were two clusters, but when we use multiple dimensions, and rather when we included more dimensions to it, then we have seen that the clusters have increased, and you can see that there is distinction between various codes. Now, what is the best example as far as the engineering is considered when we are applying supervised learning is the anomaly detection. So, consider that you have a vibration of a machinery, you are measuring it in time series form. So, you have time or number of days on x axis and acceleration on y axis. When you see this data set, there are no labels available. Am I correct? So, what you will do is you will try to identify the similar characteristics in the data set. So if you see the range of acceleration with this zone and with this zone, they are very similar, because let us consider a range as feature. It ranges from 20 to almost 30. Am I correct? So this is the common characteristics in the data set. But then when you add, when you consider the range of this particular zone, it has jumped from 30 to 32.5 and then till almost 38. So in industry, and unsupervised learning is used for anomaly detection. Okay, so when you have only data set, there are no labels available. You can make clusters out of data set. So you will make one cluster of normal behavior, which tells you that whatever operation is going on, it is normal. And if you see any abnormal pattern from this learned normal behavior, so anything which deviates from normal behavior is considered to be an anomalous behavior. So this unsupervised learning algorithm will automatically make another cluster of an anomalous behavior, and it will flag this as an anomaly. To explain this further in simple way, if you have installed fan newly at your home, there are no defects in the fan. Your brain is trained to understand that there is no noise coming out of that, as rather sound. Let us consider it to be a sound. So there is no sound coming out of fan. So your brain is trained for 2 years, first 2 years, as the fan is normal. So your brain has already made a cluster which defines what is the normal fan. Now, after 2 years, you start hearing sound out of it, erratic sound out of it. So your brain automatically flags that, because your brain already understands what is the normal fan. Now, when you observe erratic sound out of it, your brain tells you that, okay, there is some anomaly present. So this is how unsupervised learning algorithm does. But it will not tell you what does that anomaly mean, or that anomaly is specifying what kind of failure, that it will not tell you. So what you will do is you will call an electrician will come, he will dismantle that fan, he will check that fan, and he will tell that there is a failure in the bearing. So whatever erratic noise now that you are hearing is now being labeled by an electrician as bearing failure. So see, this is how the labeling process happens in industry. Labeling is to be done only by subject matter experts. It has to be done by only domain experts. Am I correct? So once the label is available, then you can go for supervised learning and you can build that model. Once that model is trained, next time when you hear similar kind of erratic sound from fan, you need not call an electrician for diagnosing the fault, because you are now machine learning supervised model, classification based model itself will tell you that there is a bearing failure. Am I correct? But of course you will call an electrician to fix that problem. So by applying this two supervised based two machine learning based techniques as supervised and unsupervised learning, what we have learned is that they can directly applicable for the domain of fault diagnosis and condition monitoring, and even for the anomalous behavior, anomaly detection as well. Now let us go ahead. We have understood the curse of dimensionality. So we understood that when we used only one color, or rather only one dimension in clustering of fruits, there were only two clusters. But when we added the dimensions, we saw that the number of clusters have been increased. Similarly, if you see these images, if your training data and the features, if they are not sufficient to classify these images either as a dog or a cupcake, or a mob, or a dog again, or a donut, or a belly, then this is the universal problem that people see in the world because of AI and machine learning. To simplify this slide or to explain this in one line, we call it as garbage in, garbage out. If you supply garbage to machine learning algorithm or AI, it will also give you garbage out of it. And that's why one thing that you must understand is that domain knowledge is very important in current age as well. It is not that AI, machine learning, and generative AI is only going to, reveal the truth, but uh, this all techniques are based on whatever data that you give, and understanding of data is only can be expected from a domain person or domain expert. That's why understanding fundamentals of physics, engineering, their laws is very important. People have started forgetting it because they feel that if you use ChatGPT, write a code and show some results, that is going to give you job in industry. Please trust me, this is not going to happen. This is the picture that being portrayed in the surrounding in very large perspective, but this is not true. Along with this AI, machine learning, and generative AI knowledge, or any contemporary tools or methods, you should also have a solid fundamental knowledge. Then and then only you will be going to survive in the industry. Now let us move ahead to the problem statements where there are no labels available, and how are we solving this problem. So you can group 3D printed surface textures into natural clusters using roughness profiles, waviness patterns, and the microstructural features. Then you can also go for discovering the common geometric feature patterns in complex CAD models using curvature maps, surface patches, and mesh descriptors. So when I was reading this problem statement from some of the research paper, I was really wondering that how far we have, we have come. I remember it 5, 6, 7 years back. We were just introduced these topics in our labs, but now when I read this, a problem statement and research topics, I really feel very motivated because if you read this problem statement, it includes the end-to-end philosophy starting from mechanical engineering to its digitization. The third problem statement, if you see, it has cluster. You can make clusters in situ thermal histories from laser powder bed fusion builds using layer-wise temperature fields to identify the recurring thermal behavior modes. The next is organizing point cloud datasets from 3D scans to shape families using distribution statistics, local descriptors, and the surface normals. So similarly, I have listed the many more statements. You can just go through it. I have to cover more topics. We have next is association rule learning, where we try to find out the association between the input and output. If you see this particular example, we have listed some of the transactions from some supermarket. So when you see this data set, the first work that you will do is you will try to identify what is the total volume of data set, which is nothing but summation of all these products. Second is you will try to identify the unique items, unique products, which can be it will be a apple, banana, water bottle, a donut, and an orange. Then you will find out frequency of each of these items. So you will see how many times the apple is being purchased. So frequency of apple will be equal to 4. Then frequency of banana will be 3. Frequency of orange will be 2, and frequency for bottle and this donut will be 3. Then what you will do is you will keep some threshold to frequency. As let us consider that product with frequency 2 and less than 2 will be omitted. So what we'll do is we'll select products only with frequency more than 3. So we will select apple, banana, water bottle, and donut. So when we go to the next slide, you will see that the first layer is consisted of an individual product that has been purchased. So since only 4 products were having frequency more than 3, That's why you can see that there are four nodes. Am I correct? In the first layer, you see that there are four nodes. First node has apple, second has banana, third has water bottle, and fourth has donut. If you see the second layer, you will see that the combination of these all four items with respect to the probability of two. So you can see that each node, you will see the combination of two products. Am I correct? So when we take the combination of these four products with the number two, there will be six nodes. Am I correct? So we have six nodes in the second layer. If you see the third layer, we'll have the probability of three. The items which is being purchased with the quantity with the probability of three. So we will have again four nodes. And if you see the last layer, we have only one node because there will be only possibility that all four items will be purchased. Now, if you observe this overall picture, you will find out that this has become a network. Am I correct? It has become a net. And this is what is the motivation behind artificial neural networks as well. Because in artificial neural networks as well, you see that there is an input layer, there is output layer, and in between input and output layer, there will be hidden layers. Now, when we try to link it to an artificial neural network, when we make this network, the next step is weighing the each node. Am I correct? What we do in ANNs is we try to we try to assign the weightage to each of these nodes from 0 to 1, suppose, and then we try to find out which of the combinations of these nodes have the highest weightages, and accordingly you try to stock your products in supermarket in advance to avoid the scarcity. So how do you assign the weights? You just go to the previous slide again. You try to find out, is there any transaction where only apple is purchased? No. Is there any transaction where only banana is purchased? No. Is there any transaction where only bread is purchased? No. But there is a transaction where only water bottle is purchased. So what you will do is you will assign a more weightage to node number 3 as compared to node number 1, 2, and 4. Then you will identify, is there any combination out of these 6 nodes which is actually available in the transaction, and you will assign more weightage to that. Similarly, you will do it for the third layer and fourth layer, and this is how you try to identify the links between various nodes, and you try to just map. And that's why I usually feels that the artificial neural networks have been evolved from such kind of concept itself. So if you see the basic structure of ANNs, it includes input, output layer, including the hidden layers. We have a feed forward a neural network where the information will be flowing only in single direction from left to right. There is no back propagation, there is no feedback, and that's why it is considered to be a concept for feed forward. Then when we have a feedback loop where whatever outcome that we get in the last layer is again feed it to the hidden layers and the weightages are changed, then it considered to be a feedback network with back propagation. Now, why back propagation is important? If you see this particular picture, it says this guy asked another guy, is this your machine learning system? Then and you can see that there is a big kachra, on which this guy is standing, and this kachra is labeled as data. And there are some answers that you're trying to identify the answers from data set. So this guy says, yes, this is my machine learning model. You just pour the data into the big pile of linear algebra, then collect the answers from the other side. Then he asks again, what if the answers are wrong? Then this guy says, just stir the pile until they start looking right. So that means retraining your machine learning model again and again is the only solution to get to reach to whatever outcome that you wanted. And that's why this back propagation is very important, because it tells you that the reiterating the process again and again, retraining the process again and again is only going to help identify hidden patterns out of data set, and that's why this is very important. Now, when you add number of hidden layers in between input and output layer, it becomes a deep network, because if you see that the network has become very deeper, and that's why it is called as a deep learning based artificial neural network. Nothing different than it. Difference between the previous network and this network is this network has more number of hidden layers and nodes, and that's why the length or the width or depth of network increases, and that's why it is called as deep learning based neural networks. Now I have some problem statements where we try to solve these problem statements using association rule learning or neural network based approaches. So you can discover a frequent combination of FDM print parameters associated with width, quality, surface finish. Then you can also extract common material parameter associations, where ABS with higher nozzle temperature or PLA with lower bed temperature kind of things across successful FDM prints. You can also discover the association between laser scan parameters and porosity zones in metal additive manufacturing builds. You can also identify the link patterns in powder morphology changes with respect to particle size, circularity, or satellite count with multi reuse cycles. You can also find coupled thermal history segments that frequently appear together during LPBF builds, indicating the characteristics melt pull regimes. Uh, then I have listed again few more statements. Now let us come to generative AI kind of concept, which is being evolved a very lot. We have already seen what is AI, machine learning, deep learning, and we come to generative AI. So the first three techniques will get the data set, it will analyze the data set, and it will give you some output out of it. But as far as generative AI is considered, it tries to generate new contents by learning out of existing data set. Now to simply identify this, we have already aware of what is the meaning of a generation, because when you start typing something in Google search bar, now here you can see that what I have typed is what is the definition of, and then the next word of it has been automatically predicted. So generative AI was started with this kind of predictive search, but it was not just prediction of next word, but it also completes the outcome that you wanted. This is how the prescript predictive search differs from generative AI. Because if I started writing an email, if I write 4 words, predictive search will give you next word to that statement and it will stop. But if I ask ChatGPT to write a complete email based on 2 sentences, it will not just predict what is I'm going to write next, but it will give you the complete email. This is the main difference, and this is how the generative AI has evolved from old school, which is called as predictive search, and it was actually started by Google. So when we come to generative AI, there are foundational models, including large neural networks. Then there are large language models, which only deals with texts and the languages through text. And then there is a application, developed by OpenAI, which is considered to be a GPT, where G stands for generativity. It models to creating a new contents. P stands for pre-training, where it trains a lot of naturally occurring data. And T is the transformer, which is considered to be a core of this application as artificial neural network architecture. So if you see the building blocks of generative AI, it has the prompt, which is input text. Then it has a model, which is considered to be a huge AI system. And then we have a generated text, which is considered as output. Now, this is the penetrative AI case study that I wanted to tell you, because most of us, we are using ChatGPT only to write email or solving our doubts. But ChatGPT is nowadays also used for correlating it with whatever going on in the environment. And the chat, what research they are trying to do is they are trying to extend the capability of large language model to interact with the environment and also reason about it. Okay, so the best example is given here. So there is some liquid which is being heated. Am I correct? And there is a thermocouple mounted to measure the temperature of this liquid. Now, the output of this thermocouple can be supplied to this chat GPT in 2 forms. Either you can give the digital signal as it is, or you can convert it into a textualized form and you can give it to this large language model. Now, when you see this prompt includes the temperature information, and along with that temperature information, you are also providing the knowledge, expert knowledge. What is the expert knowledge? The boiling point of water is about 100 degrees Celsius. So this shows that when sensor output data is being supplied to ChatGPT along with expert knowledge, ChatGPT is actually able to interact with this physical environment, and it is actually giving the output describing the physical state as water is boiling. And if you ask what is the reason of giving this output, it will tell you that I have used the expert knowledge. So it is using the reasoning that when the expert knowledge is saying that boiling point of water is this 100 degrees Celsius. So this is how this AI systems, I know people are nowadays, they're trying to use this to interact with the environment. Now this is the very simple example, but people are trying to use it for even typical engineering applications as well, where they're trying to evaluate the capabilities of large language model to solve even engineering problems as well. Now, to narrate this example, let us go to a depth. So you see that there is a girl who is walking outside and she has a smartphone. So what we have to understand from this physical world example is there is a presence of girl. Second, that she is what is her motion, and the third is where is she. So three things we need to interpret from this example is first is the presence of user, second the motion of user, and the third is the environment. Now we will use smartphone which has various MEMS based sensors such as accelerometer, then the gyroscope, and then the satellite information, and we have also have Wi-Fi. So when we supply this sensor data to large language model will give you description as user is walking in outdoors. But you will surprise that how large language model has actually identified there is a presence of user, motion is she is walking, and the environment is outdoors. This example tell you that how should we formulate our problems when you provide ChatGPT output of sensor signals along with the context and the prompt and expert knowledge, it will actually try to give you correct physical description. So what you have to do is you have to write down some rules. The rules can be if the step count is very less or if it is zero, then the motion is she is stable. If the step count is high, and here see here you are not giving any threshold, you are writing a general statement such as if step count is very less or if it is none, then it is stable. If step count is higher, then she might be walking, or if it is too high, then it would be that she is running also. Then you can write few statements such as for in identifying the motion and user presence and even the outdoors. So this is how the penetrative AI concept that people are trying to investigate more to evaluate the capability of large language models to interact with the environment and also reason about it. Now, this anomaly detection example that I will skip now because we have only 5 minutes. Let us summarize the use cases in additive manufacturing where it is being actually used in industry. So the Zometry is the AI coding engine where it automatically analyzes the uploaded CAD files. It determines the manufacturability. It estimates price, lead time, and assigns a process. Then we have additive manufacturing quality assurance suite by Siemens, where the sensor data is used to detect the defects, anomalies, thermal issues, and process deviations during the metal additive manufacturing builds. Then we have EO state monitoring, which tracks the melt pool, detects patterns, keyholes, porosity signatures using real-time imaging. Then we have blacksmith, where it compares the part scans to CAD. It evaluates the deviations. It predicts the structural performance, generate QA reports, and so on. A very famous generative design suite available by Autodesk Fusion, which automates the topology optimization, lightweighting using AI to meet engineering constraint. Then we have internal AI knowledge systems by Siemens and GE. which enables engineers to search technical documents, best practice guides, and parameter databases via natural language. As far as the more use cases are considered, we have materialized by HP 3D production suite, which distributes the job across multiple printers to minimize the downtime and maximize the throughput and cost. It reduces the cost. Similarly, we have GE Additive and NIST collaboration tools where it tracks powder reuse, contamination, morphology degradation to maintain the metal additive manufacturing quality. And there are a few more I have mentioned. Uh, so let us now summarize the challenges, because we have talked a lot of things with applications, methods, approaches, and so on. But this is the real slide where I want most of your attentions, because these are the real type problems that we all face when we build machine learning based or data driven models in industry. So as far as technical challenges are considered, we have limited availability of high quality labeled data set. We have high variability in additive manufacturing processes across machines, materials, and vendors. As far as sensor data with thermal and optical cases are considered, it is very noisy and it is difficult to standardize. It is difficult to model complex and multiphysics interactions in processes like LBBF. And nowadays, physics-based machine learning, that's why it is being evolved. Or neural network-based machine learning models are also being evolved to solve such kind of problem where we are trying to fuse physics and machine learning, or first principle models with machine learning and so on. Then there is a lack of real-time feedback loops for AI control printing. Integrating AI insights with existing slicers and CAD workflows is also considered to be a lot of concern. There is limited generalization of machine learning models across this particular domain. And the data privacy and proprietary constraints remains a very big problem, irrespective of whether it is additive manufacturing or anything related to that. Then, as far as operational and industrial challenges are considered, additive manufacturing environments are not yet fully digitized in many facilities. When I say they are not digitized, the data that you expect in the input is not being, collected, and that's why you're not able to build machine learning models out of them. Then there is a concern of large data storage and compute requirements for high-speed imaging in metal additive manufacturing. It is difficult to align AI recommendations with operator expertise and workflows, where actually large language model-based techniques are now playing a big role to break it down into a simple language where the operator can understand it. Then there is inconsistency in print logs, and incomplete historical records leads to falsification of data, and thus the machine learning model will also throw garbage out of it. Cost of instrumentation, as far as the images are considered, is a concern. But if it is non-image based sensors, then I think we have a good opportunities nowadays because of MEMS based technologies. Because the accelerometer, MEMS based, any kind of sensor can now you can get it in within 500 rupees or so on. So at least you can build a prototype out of it. Of course, explainability again is a problem, not just in application of AI in additive manufacturing, because rather it is everywhere. Because only decision tree, support vector machines, and other few algorithms are able to explain the reasoning behind them by showing the explicit rules. But the big black box model is considered to be a neural networks, because they're not able to explain the reasoning behind it. LLM specific challenges we have. LLM hallucinates incorrect technical information many times. They have lack of domain specific training data. It is difficult to embed large language models into CAD slicers and machine controls reliably. Maybe within next 2 to 3 years, this problem could be solved, because people are extensively working on integrating large language model at edge level, and they're trying to integrate it with the smart machines and other any smart machine tools. Then there is need of interpreting interpretability of outputs when used in high stake industrial scenarios. And as far as standard and interoperability is considered, we have lack of universal data formats for additive manufacturing, monitoring, and logging. There is vendor lock-in across hardware and software platforms. There are no standard benchmarking for evaluating AI and large language models performance in additive manufacturing. So the scope for academicians remains in performing more and more experiments and collecting a data set to make it benchmarked and publishing in the public domain, so that industry can use it to validate whatever end-to-end algorithms that they have developed. uh, as far as human adoption and challenges are considered, there is a gap between operators, faculties, and engineers, which requires new training. Because in industry also we see that we require a rigorous training to employees in industry to adapt these new changes. Because unless and until they make comfortable with these techniques, it is impossible for them to understand what is the significance of this. Uh, then there is some resistance to replacing traditional workflows with AI-driven workflows. In some cases that I have seen in past 2 to 3 years, there are trust issues when AI suggests process changes without full transparencies. This is the big problem that we see in our industry, because uh, people are not ready to take these things so easily to, as considered to be an option to whatever they are doing. So it is a big, again, open area where people can work. That gaining a trust on these techniques is also equally very important. And of course, the last is there is a need of interdisciplinary understanding of materials design and data science as well. With this, I would like to conclude my session. Thank you so much for this opportunity. I hope I have concluded it within time. I have given my mobile number on the screen. If you would like to connect with me, you can just send me your name on WhatsApp, and then we can connect. And if you want to connect with me on LinkedIn, you can just scan this QR code and we can connect. So thank you so much. I hope I have given some insights. Then
Yeah,
you have
thank
left.
you. Yes, definitely. Thank you, Dr. Abhishek. It was
Uh,
wonderful talk. I was just, listening to you from the first second you started, and the way you carried out, this particular entire session, giving the, what is AI ML, and bringing it to the 3D printing, and how this is fused, these two contemporary technologies is wonderful for the diverse background of the participant, and that is much needed, because the participants are from various backgrounds, various disciplines, and you sailed so good. Okay, only in interest of time, because already Dr. Vinaya, the next speaker,
yeah.
already logged in, and with the due permission of Dr. Vinaya, I can take one or two questions from the participants.
I just
Absolutely,
want
absolutely.
to, sir, I just want to show you one tool. I
Ah,
just need 1 minute, because that is the most
yeah.
important part that I have actually forgot. It is
Okay.
available. I have opened it already, so you can
Yeah,
see.
yeah. I will take consent of Dr. Vinaya. Dr.
Yeah,
Vinaya
yeah.
is fine,
I'm
because you
yeah,
see
yeah,
your
yeah, I'm
time now
okay.
from 3:30.
No,
Yeah.
I'm comfortable with the time, so he can take.
Okay, I just
Okay.
need 1 minute, not more than that. Okay.
No worries.
Okay. So now if you see my screen, I have just
Yes, yes.
typed
Please proceed.
Leo CAD Copilot on Google. Okay. So when you see the first website, it says engineering grade AI built for leading engineering firms. So when I click on this website, you land to this particular page. So this Leo Copilot is actually meant for converting your text into CAD model. So now suppose if I type 3D external gear pump, okay, and you just see the wonder. So I have just written 4 words. Am I correct? 3D external gear pump, and I'll just click on drafter. Okay. So then it will do some processing. It will just try to identify, I mean, try to search information about design of external gear pump and its models. It will create a plan. It will do some analysis, It will have design considerations, and even you can see that there are references also are given. Uh, and then it actually creates a final prompt. Now the final prompt is an external gear pump with two intermeshing cylindrical gears inside a rectangular casing, featuring inlet and outlet ports on opposite side and mounting flanges. Now here there are some options. If you want to draw something, you can draw it here. If you have some images of 3D gear pump, XL gear pump, you can upload. And there is an option from having a draft version or rendered version also. So I have just given a text prompt. Okay, I am not going to give anything, and I'll just click on generate. Now you can see that within 15 seconds, 10 to 15 seconds, three different configurations of this external gear pump will be given. And this is the magic of generative AI, generative modeling, rather, I will say, to be specific. And this is how, I think we should also think while defining our problem statements. Yeah, so you can see that
Okay.
there are three different configurations have been built.
Oh,
And then
wow.
you can just play with this and you can get whatever you want. You can also download these files as CAD files. There are various options available. You can just, I just wanted to show this application. You can see that there is a option for upscale, generate variants, generate 3D, and so on. Fine. So the name of software is Leo CAD Copilot. And if you purchase their license, you can also explore this view. You can get isometric and orthographic projections with detailed bill of material with limits, fits, and tolerances as well. Thank you so much.
Oh, great, great, wonderful. Yeah. So, uh, wonderful. Really, it was a very informative session, and so much of things you covered in this particular time. Okay, one or two questions only, and then if participants have more questions, then they can connect me, and then I'll pass on all those questions to Dr. Abhishek. So, quickly, one or two questions from the participants, they can unmute and discuss.
Sir,
Yes.
whatever process you have shown in the last LeoCAD, can we open that gear pump in mechanical softwares like
Yes.
SolidWorks? Or...
Yes. Only thing you have to get their license. Whatever demo that I have shown, it is free demo. Actually, you can log in through your Gmail or any other email, and you will get access for 6 days, which is the very basic access. But if you purchase, if you rather, you should request your HOD or principal or college to get subscription of this tool, and then you can use it. You can download it in a CAD format. You can open it in any CAD software, and you can even change the models also. If you want to do some changes, that also you can do. So it
That's
saves a
great,
lot of time,
actually.
actually. That's why it is important.
Yes, sir. Yes. Thank you.
Yeah.
Yeah, fantastic, fantastic. In similar line, Professor Placid Pereira, who is SPC alumni, professor there and Professor Emirates now, also developed one more such application named as Trinity. I'll share with participant and with Abhishek also.
Yeah, sure. Thank
Discuss
you.
separately. Yeah.
Thank
A
you. Thank you so much.
wonderful app he has also has developed. Professor Placid Pereira, professor at Illinois.
Oh, okay.
Champaign. Yeah.
Very good. Thank you.
Okay, thank you, Abhishek. Just
Okay.
want to stop here because of time only.
Yes.
Wonderful to
And
have
I
this.
will share the PPTs with you. You can share it too also. No
Yes,
problem.
definitely. Yeah.
Thank you. Thank you
Thank
so
you.
much for
Thank you
opportunity.
very, very much,
Thank you.
Abhishek. Yeah.
My pleasure.
Yeah. So, Dr. Vinaya, welcome to this session, second session. And my team will moderate initially for your introduction and all. So, over to you, Professor Deepak.
Yeah, thank you, sir. It was just an amazing session by Dr. Abhishek Patangi. It was really wonderful, sir. We got to learn various new things regarding the machine learning and the latest technologies that are going on, and how do we implement in all the existing traditional uh, process that we use. It was wonderful. Thank you, Dr. Abhishek Patange. Now, let's move on to our next session. So, before starting our next session, I would like to introduce one of our faculty participants who will introduce the speaker for this particular session. So I welcome Dr. Sachin Kamble to our faculty development program. Dr. Sachin Kamble is working as an assistant professor in the Department of Chemistry at Sanjay Godwat Institute, Kolhapur, Maharashtra. Currently, he is serving as a Dean of Research and Development at this institute. His research interests include material science, nanotechnology, energy storage, and catalysis. I once again welcome Dr. Sachin Kamble to the FDP program. Thank you, sir. Over to you, Sachin, sir.
Thank you, Deepak sir, and thank you for this opportunity to introduce today's guest, Dr. Vinaya Manvatkar. Let me introduce her. Dr. Vinaya Manvatkar is a design engineer and additive manufacturing specialist at Eton Limited. She has 16 years of experience across advanced manufacturing, engineering, design, and research. At Eton Limited, she contributed to additive manufacturing initiatives, engineering project leadership, and technical oversight within power management sector. Prior to Eton Limited, she served as an assistant professor at Sardar Patel College of Engineering and contributed to engineering education and academic development. She has completed her postdoctoral studies from Penn State University, focusing on research driven advancement in manufacturing and engineering systems. Earlier, as a scientist B at Samir, she developed complex mechanical systems for microwave applications. About her education, she holds MTech from IIT Kharagpur. She holds BTech from VJTI, and she is a CII certified professional in carbon footprints, demonstrating a strong commitment to sustainable engineering. Her area of expertise includes additive manufacturing, mechanical system development, design engineering, fabrication, and hands-on implementation across research and industry environment. So we are very pleased to welcome Dr. Vinaya Manvatkar to this 1 week FDP. Thank you, and over to you, Deepak.
Thank you, sir. Now, ma'am, please, you can continue. Vinaya, ma'am, over to you,
Thank
ma'am.
you. Am I audible?
Yeah, ma'am, you are audible. Please continue, ma'am.
Sure. Thank you, Professor Bole, Professor Deepak, and Professor Kamble. And thank you for this nice introduction. Let me quickly share my screen. Is my screen visible?
Yeah, madam, it is visible. Please continue.
Yes, it is
Sure.
visible.
Okay. So I think all of you had a great sessions
Just
listening to different
put
topics.
presentation in presentation mode. Keep it in presentation mode.
It is just give me 1 minute. Hmm,
Press F5, madam.
just give me a. Is it going in a presentation mode? Because I put it from my side, it is on the presentation mode. Can you just check?
Not yet. I think what you do, you come out of the presentation,
Yeah.
again do the share, and while sharing, you put entire screen. That will work.
Okay. Just give me 1 minute.
झाला का टाइम तर दाखवा मग.
Now it's perfect. Done. Yeah, Dr. Vinaya. You are mute.
Can you confirm I'm audible
Yeah,
and the
you're
screen
audible.
is in full screen?
Full screen.
Okay,
Yes.
perfect.
Perfect.
So I hope you would be enjoying this series on different topics on 3D printing topics. And I'm sure, I mean, I was hearing to the previous speaker, and he has covered in situ monitoring and data mining things in the 3D printing. So everyone has, you know, covered most of the topics in bits and pieces, and what I'm planning to cover, how those are being used in industrial context, and what are different aspects that are considered when we use 3D printing in the industry. So it's about me. Already Sachin sir has covered it. Uh, so I'm currently working in Eaton India Innovation Center. This is my recent experience in Eaton. Initially started as a lead engineer with Eaton Research Lab, where I worked on the process optimization, process analysis, and sustainability assessment for additive manufacturing. And now I'm a part of aerospace team as additive manufacturing specialist, where I work on the different applications catering to different divisions of aerospace. And professionally, my journey has been in academic profession is on mechanical engineering, then manufacturing sciences, and going deeper into the additive manufacturing analysis topics. Today, I'll be covering additive manufacturing, where and why, what it is from end user points of view, what is the factor in influencing when selecting aim as a manufacturing process for products, what are different developmental stages, developmental lead needs, what are aim roles and skill set required, and current trends. So initially, I'll just cover briefly on as a refresher additive manufacturing. So as a ASTM 52900 standard, additive manufacturing is a process of producing part layer by layer to get a part defined by its CAT, as opposed to by material removal process. Here there is a material addition, so it is additive manufacturing. There it is divided into 7 classes of processing based on material input form, whether it is powder, liquid, or in the wire form. What is the material processing arrangement, whether it is spread in the tray, spread it in the powder bed, or it is coming down through nozzle or extruded through wire, and the energy sources, whether it is light, electron, and laser. And this process is there for quite some time. It started around in 1980s with SLA, and it's growing since then. We have SLA, FDM, now DED, E-beam, LPBF, and now there are bioprinters, large format printers. So technology is evolving, getting bigger. So that's its journey. This is brief on the process and its terminology. You start with a CAD model, then it is virtually in their softwares. Probably you are using GrabCAD or Insights, those kind of things. Even some of the CAD packages have the slicing packages inside them, Magics. Then it goes to the machine software, where it defines its tool path, very similar to the CNC machine. Then actual programming is done. It prints the part, it cools down, you have to take it out from the build plate, and you get a near net shape part, and then it goes to the post processing. And here are some commonly used terminologies which I would be using in between my presentation. So it's CAD file, material layer, recoater blade, heat sources, support structure, build chamber and environment, build platform and its location. So this is a basic background on AM technology. So what are the typical drivers when AM is used in the industry? There are market drivers and there are some benefits which is for the user. Market drivers are mass customization because uh, you need something new every day. So very nice example which is there on the internet is, we wear the shoes. You want to make it lightweight, we want to make it bouncy, so we add a lattice structure, different materials. So very fast customization. So that's the one. Then these designs are digitally enabled. So how we can quickly get it done. Advanced business models, supply chain dependency and resiliency towards it, low market entry barriers, geopolitical disruptions. So you want to, based on that, you want to develop in certain regions and reduce those cycle times, and distributed manufacturing also leads to the lead time increase. So these are all market drivers. When we come to the use, it is what it offers is improved performance, cost out, reduction in the cost, trade secrets, the recipe is in house. Since it is a near net shape, it reduces the post processing cost, medium volume production, light weighting, complexity for higher efficiencies, and many other benefits it offers to us. So let's get into its individual benefits, where it comes from. So speed. So it gives me rapid production development. Since it is a near net shape, it it actually eliminates tooling fixtures at some of these stages. I will not say every stage, but some of these stages. So if you imagine casting or molding, so you have cavity and core. So some of the toolings are developed. Shorter lead times, lower cost because some of the materials are difficult to process or machine, and it goes costly, and also it produces scrap. Here you just selectively use material, and that is the only material which is utilized, and the remaining material is reused. You can always take the decision between repair or replace. You can keep reduced inventory. When it is a reduced inventory, is the availability of the product or the raw material to kept inside the campus, and when you keep more inventory, you have to maintain it. So reduced inventory, reduced maintenance, uh, lowers the cost. Part consolidation, so bigger system or complex part can be consolidated to one, uh, which lowers the cost because BOM is reduced, but at the same time it also increases the reliability because of reduced interfaces. That goes into the improved performance. So where we have efficient design, weight optimization, we reduce the packages. And as I said, there are supply chain benefits, reduce supply chain benefits and sustainability benefits. These are the certain offerings from AM. So how the end user distribution look like? That there is at least no industry untouched by AM, from automobile, aerospace, electrical, medical, marine, construction, consumer goods, everything. And here are some examples. In automobile, there are holders, chassis components. Uh, in aerospace, there would be housing, holder, brackets. In electrical, there are connectors. In medical, there are implants, and so on. And every industry have achieved some or other benefit from some of the listed one. What differs in the industry is the certification and the qualification. It is every industry is guided by different certifying or qualification agencies. Like for aerospace, you have FAA or ESA. Electrical, you need UL certification. Medical, there are others. So every industry is guided by certain requirements and its certification. And based on that, the testing, qualification, development is needed. So how the general industry architecture look like here? So there is a system manufacturer who provides the complete system. Then there are tier 1, tier 2 suppliers. So if you imagine an aeroplane, so it is a system which is given to the airlines. The the complete aeroplane gets components from different suppliers. This supplier also gets some standard parts. You can imagine nut, bolts, washers, and a raw material if they are manufacturing part in house. And then it goes to the buyer and engineering services. And this is how the general architecture look like. And buyer, except buyer, most of these or some or other way can utilize AM in some form. And what happens is you need a stronger supply chain to maintain the flow. So what happens? AM offers the easy transferability. So if I have made a part at certain location and I need it in the another location, you have to send a CAD file. If it is the same system, same process parameter, you just print it and it makes it available. So this helps the easy transferability, local manufacturing, and just-in-time production availability. So from here, I'll go to how the product development and process development look like. So I'll take a pause here if anyone has any question. Sure. Okay. Thank you. So for product to be printed and accepted for the production, there are different stages involved from machine buying to the final production of the part. So when you buy a machine, it comes up with a setup. It comes up with a given quality that OEM offers you. So one has to do the machine acceptance and process verification. So what is given and claimed by the OEM is really happening. So once you have that, you try to develop, then to accept the machine. Then you do the process specification development. Process specification development involves the process parameter understanding, quality understanding, printing of multiple coupons, what it is given, data analysis, and understanding what is the mean and variability of the process look like. And then you develop a recipe to give you a certain quality, and that is then frozen, which is called qualified metallurgical process. It is a material specification development, and then that recipe is used in the product to develop that product and expecting certain quality of product. The product development involves design for product for performance, its requirement, what its functionality is. Then it is designed for AM. For other processes, we call design for manufacturing and assembly. Then the multiple builds are done to see the consistency of quality and its performance, and testing happens, and the final design is then design, and build orientation file is locked, and even the material properties and variabilities are locked, and then it is used for the final production. You have certain checks, which is PPAP, pre-production approval process, qualification testing, and then it goes to lower scale production and scale up. So understanding of process, material, and part design is very, very critical to develop the confidence of the production and on its confidence. And it is done through multiple controls, measurement, and continuous analysis of data. We'll go to now individual bucket, what is material and machine qualification would look like. So under material and machine qualification, so in machine, it's a process. So here I have given the example of LPBF process, which is metal powder bed fusion. Use laser beam or electron beam. Here the LPBF is laser beam, or you have a electron beam processes as well. And what is its inputs or the parameters look like? But this process generally applies to any aim process uh, you would decide to use. So in this process, what is the input? Powder and parameters. So in material, one has to decide the material quality that is acceptable based on the right side, the output of the printed specimen. So you would print a specimen based on ASTM standards, based on what properties you want to measure, whether it's a physical properties like density, thermal conductivity, or those type of similar properties, mechanical properties like yield strength, elongation, ultimate strength, electrical properties, and metallurgical characterization, porosity, what are the phases. So there are expectations of these properties based on the product requirement, and the process input parameters are optimized or designed and decided in such a way to get these properties at mean and mean values, minimum acceptable values. So for powder, it is powder particle size distribution, its tap density, its composition, and its form. And on the printing side, what is the laser power? What its variation required and its impact? What is the layer thickness you go with? Will you go with 40 microns, 70 microns, 100 microns? What is the hatch spacing? Hatch spacing is basically distance between two lines, and the processing environment, which typically alters the cooling and general atmosphere inside, because as you know it will form a soot when it melts, so it also carries as a cooling and the soot carrying environment. So once you decide this parameter, you design a design of experiments, you print coupons, required coupons with that, and you do the testing and see what is your mean and the variability look like. And it is not the one time one build activity, you have to do it across the build, so you know what is the robustness of the process look like, you know how long my process gives me consistent output. Because of that, there is something called as preventive maintenance. Every OEM suggests a preventive maintenance of the system, so that uh, with usage there is a possibility of hardware or those kind of degradation, so you reset it back. So that is how you decide your operating conditions and raw material acceptance conditions. Once you finalize that, you do it over build, and you track it over the time how the consistency look like, and freeze those parameter for printing specimens. It is still on the coupon that you have to understand. And when you go on the product development, you also have to understand based on the product design, whether it is thick, thin, longer, slender, inclined, those consideration will come into picture while deciding its critical to quality parameters. It can be dimension, it can be surface roughness, it can be mechanical properties. So once at the development stage you print it, they will be always compared with the benchmark specimens, which is acceptable, and appropriate changes are made. And once they come within acceptable limit, those design files are logged. So initially you log the process parameter, you got the properties, and the second stage is the build files are logged. What does build files include? They include the part files, its a location on the plate. Now there are single laser system, multi laser system. So which a laser should process that, whether it should be one laser or two laser operating on the same part, and what is the sequence look like, even the support structure strategies. So these are the parameter which are typically decided here, and any changes for DFM done for the product. Once these tools are frozen, you go to the production quality, and during the production you expect the quality which is decided on the at the product development stage, that should be achieved. And for that, uh, process consistency, it's continuously monitored so that it builds the under similar condition same part again and again, which results into reproducibility and repeatability, which defines the process robustness. While saying that, all these phases are currently machine and material specific. the designs are product specific. Its orientation, location, support structure, it is very product specific. And assessment of the mean and the variability of quality is very critical. And one has to assess its impact on the product performance. Now, from the lens of end user, when we accept it, these are the dominant question we need to ask ourselves. Why am I using it? Is aim feasible? What is the is it saving my time? Because while implementing, it has its time impacts at different stages, and all of this, how is it impacting the cost? So why am I using AM? Do my current manufacturing is giving me any challenges? Do I have supply chain challenges so that I want to reduce the dependency? Is my product having low volumes where I don't want to invest in tooling and hence longer timelines? Is it a current product conversion or is it a new product? Is there any possibility of innovative designs which is probably restricted by current manufacturing process? Is it covering my portfolio? So if I'm developing it for one product, can it be translated to other designs as well? And what are other benefits it can give me? Is aim feasible? So it will depend on what my part geometry is, material requirement, and suitability of process. So size of my geometry, even features on my geometry. Big so current envelope is I think 1 meter by 1 meter kind of thing, and a multi-laser system. Is it fitting into that? And is it okay to use that system because of the investment it has? Or do I need to go for the smaller system? And in that smaller system, do my part fit? Material. If we are very material specific, there are limited materials currently available. So there is so the available material, do they suit my requirement or do they serve as an alternate material for the currently selected material? And based on the available process, is this process suitable in terms of giving me resolution, feature size, production rate? So sometimes it is, if I have to give you example, wire based system give the higher production rate, but if I need a finer resolution, those are contrasting requirement I have, and sometimes it may not suit. So these are the three things which primarily decides the possibility of printing. Then can it be made usable as a build or through post processing? Can I use my part as printed, cut from the build plate and directly in the use? Or does it need any post processing? It can be heat treatment, it can be machining, it can be polishing, it can be just tumbling. Or if there are internal passages, then cleaning of those. The does printed by satisfy my CTQs. CTQs are critical to quality requirement, and it can be dimension, surface roughness, uh, and even the properties. And are those CTQs achievable as printed or through post processing? Extent of process development required. Is material developed for it? Are process parameter developed for it? Then my cycle is smaller for realization of product. But if the material is available for printing, but if I have not developed my process parameter for the production, then that cycle becomes longer. And all these things is at what cost? Then what are the costs involved? There are investment in terms of machine, in terms of development of coupons, reaching to certain TRL, MRL levels. Then when you go to the development, then it is a product development, qualification and certification of that product, even the maintenance. These are different costs are involved, and those needs to be accounted for when we calculate return on investment. And the last is time. So you have development time, uh, it is process and material development, product development, pre and post processes. Though they are available, they may have to be developed for the specific product and quality requirement. The quality as the output quality of the printing. Inspection, qualification, other lead times associated with the VSM, value stream map, and time to market. So all these components needs to be assessed while deciding uh, aim suitable candidate. So when these things are done, all these stages can require 2 to 7 years of component development for AM till commercialization. Depending upon which industry it is, depending upon what qualification extent it is. Material qualification itself can take 6 months to 3 years, and development cost can go from 100K to 800K USD dollars for very critical application. So development and approval of AM components is multi-level and multi-layer efforts. Any question at this time? Okay, thank you. So we will still want to reduce cost, time, and resources utilization while maintaining the quality same. So what one will try to, on the process side, one would try to reduce the printing time because that would eventually impact the uh, cost. So how will you reduce printing time? By optimizing process parameter in the existing system, going for higher layer thickness, and based on that, optimizing the other parameters associated with it. Second is bigger envelope machines, multi-laser systems which can uh, create multiple parts or larger part at a time. Then support the developmental effort by scientific approach. It's analysis, digital design. So whatever iteration one has to do, one can utilize the digital tools. And so at the digital, it is a cycle. You design a product, analyze it for its performance, design it for the aim, and see there are multiple aim process simulation softwares that one uses, and see it for success or failure. Any trends it gives that build may not be a success, go back, change the either build design or the product design, and reiterate it till it goes to the uh, safer zone. And then after that also you will have 1 to 2 iterations of building where um, you will assess the quality what you have achieved. Then in process monitoring and control, uh, image processing. So what you do in process monitoring, you capture either images or signals given by the sensors in a built in inbuilt in the chamber, and you see if your all the processes all the process health is fine. And on the fly, if you observe there is any hiccup, either you would try to adjust that parameter. If I have to give you an example, if you see there is a recoater hit, my part is bulky and it is distorted and it is probing out of the layer thickness, and it indicates me there is recoater hit. And either you take a pause and with the recorder you take some actions, or sometimes if there are multiple parts, that particular part can be removed from that location virtually, or tell the machine not to print that part, print other parts, so you can save on the time of that build. If that is not possible, definitely one has to do the course corrective actions. And then overall optimization uh, of the VSM. VSM is value stream mapping. You plot from raw material input to the final product. What are the processing stages involved? And you align those so that you always get first pass yield, first pass success. use of NDT technologies so that there is a less destructive testing, and also with the digital tools during development and qualification testing and procedure, one would want to qualify majority of the things by analysis or similarity because it was already done or tested on the coupon level or part level, and just do that is the expected qualification, which cannot be done for the other two procedures. Now, once we understand the overall scope and how the work uh, or testing or different aspects of aim and what are the different stages involved, their considerations, there is another one important question, whether I want to do manufacturing using aim in house, or do I want to use something which is available in ecosystem. The questions that we would answer is my application prototype, product, tooling, or repair? So how frequently I'm going to use it? What is my utilization look like? Whether it is one of a kind. Am I going to, is it going to be useful for me in future? So based on that, it's very important whether to do that much of investment. Does my portfolio support my ROI, return on investment target? Whether it is 1 year, 2 year, 5 years, 7 years, those are the things. Whether my investment, am I able to recover it? Which technology is most suited for application? The technology is growing. So does my application demand more LPBF technology or EBM technology or wire additive manufacturing? Even it is a decision between the metal technologies or polymer technologies. So which is the most suitable for me? So I will in-house the most utilized one for my product. For the remaining ones, probably I would develop somebody which has the capability and certification and work with that. And do I need one technology or multiple technologies which are supporting? When I decide to utilize the ecosystem, what are the checks and balances? Availability of ecosystem for printing, where it is, and with that ecosystem of printing, whether pre and post processing is also available around, or there is a connection, because every unavailability is going to cost travel of that component, and this is going to lead to lead time increase and a cost increase. Traceability of process consistency, it is very important factor uh, in the production and the process product development is traceability, because any failure in the regular thing, you can always go back and see what was the powder lot, what is the parameter I printed with, how did I do, what was my orientation to print, what was my orientation to remove it from the bill plate, how did I machine it, which machine I used for the machining, which heat treatment, during the heat treatment how do I how was the orientation, even the traceability of the temperature inside the heat treatment, and all the availability of data which is very specific to individual component can help us solve the problem of the failure if it occurs, which is called root cause analysis, and which needs to be eliminated and which needs to be restricted from happening again. That is why the traceability is very important. Then how is the technology development and transfer look like? Will the ecosystem or service provider going to develop the technology and then transfer it to us, or it is going to be with him and we are going to utilize it every time we need it? Then how is the hardware and software consistency for quality and reusability and repeatability is maintained? Because if hardware changes and software changes, it does have impact on the product quality, and how the transferability and consistency is confirmed, and is management of any system and material is tracked by the service provider, So these are a very, very important aspects. These are carried out in house also, and it has to be checked if the service provider is also maintaining that. And based on that, even you have heard the certification, right? It has NADCAP certified, it is 9100 triple zero certified. So these are the certifications that facility provide based on their audits, based on how stronger their procedures are to maintain their qualities. So we talked about what AM can offer, but at the same time there are certain restraints. So there are currently challenges in the manufacturing of very large individual parts. Uh, when there is a smaller system, very controlled system, there are only one or two parts that can fit into the chamber, or it may not fit into that chamber. And then once we go for the larger machines, the part will get processed for multiple laser, and there is something called as stitching lines. And whether it's acceptance, it's qualification, it's uh, even sequencing, it is a very, very important aspects of it. Then standardization and certification of process, because since it is machine dependent, uh, and why is it machine dependent? Because that variability is yet to be checked. Once it is done, when it is standardized, it is very easily acceptable, uh, based on the confidence we get. Currently, it is limited just because that complete variability is yet to be checked. Variability checked for individual machine with the usage, with individual build over build and time over time. That has to be done for multiple machines, multiple material, multiple locations. Even for the single OEM, there are multiple very even makes. They keep on have the different versions of machines. So that needs to be done. Ensure the consistent qualities, uh, compete on cost with the traditional manufacturing. So some of the material machining is cheapest one, right? So competing with that, sometimes it's very, very difficult, even when we know there are advantage on the design side and the performance side. It still remains application specific because of features. It has low degree of automation because of the very sophisticated system and its connectivity. And scaling and transferability, it's still a good amount of effort uh, process. So what are the developmental needs, or where the development is happening? The development is happening in terms of hardware. We are trying to get the faster or high production printers, uh, which would give us the quality which is expected. The largest size in LPBF is approximately, as I said, 1 square meter, with a multi-layer high deposition rate, high-speed system which is binder jet which is coming, part stacking possibility that you are stacking one part above. So that is being slowly developed. Accessories, integrated system. Then development in process monitoring and process control, in process part quality check, in through signals or actual checks, innovative exposure strategies. Then requirement of services. It can be a printing, design platform, installations, training, digital solutions, and material development. Definitely, development of new compositions, uh, or even the very standard conventional material which are easily acceptable for uh, already existing applications, development of parameter and post processing treatments. So these are developmental needs, or these are being worked on currently. So this is a brief map of who is working in which area in terms of development. So in digital developments, there are major upgrades happening on the softwares, where the software can develop a build but also assess a build with a plugin in itself. So, and even they allow some CAD level of changes, which was initially difficult because the output is STL. Many companies are investing into new material development, hardwares in process monitoring. Hardware is being developed within the AIM printers. Component level, they are offering services. Multiple machines, post processing and printing machines are coming up with new technologies, which gives the high speed and the quality. So those are the this is a quick glimpse of development areas and who are those companies working on it. And on my right side, it is a map of what are the aspects of AM in terms of standards, materials, testing, and the agencies as a brief, handy map for all of you. So when we work in the AM industry, what are the different assignments and roles exist? So uh, needs are typically one has to develop a business case and ROI, make or buy strategies, workforce and organization structure, whether it is a specific organization working in a system or a product or multi-product or service, that kind of thing. Quality and compliance, capacity planning, process selection. If you are housing it in-house, the facility layout and infrastructure. As previous speaker said, training and skill development is must have now with the upcoming technologies. It's a digital integration uh, for automation and reduce intervention, faster solutions, and definitely and most important, safety and environment controls. So these are the kind of aspect one has to take care of, and who does it? So there is AIM program management and execution that has to be done. Then there is AIM operation management, design and engineering, production and machine operations, AIM skill development, quality compliance, safety and environment, and IT data management. These are the different teams working together. The highlighted green ones are the core AIM working systems, where the others are generally applicable to all of them. Quality, safety, IT, you know. And to work in this area, the typical skill development are very core knowledge and experience, which is part design for performance and part for manufacturing. Material processing and characterization. One needs to understand if I process my material in certain way, so what is the output look like and why it is looking like that. So manufacturing science and its operations, quality control, part and process analysis. So part analysis for performance and process analysis for success. Project planning, data science and its application. So this is the core knowledge one needs to acquire, and then this has to be modified or relearned for AM. So once you have the basic, and on top of that, working on AM would develop for AM this knowledge. So with this thought, I am reaching to the end of my presentation with the summary of current trends in additive manufacturing. It is an improvement of productivity and flexibility of existing technology, multi-material, multi-laser system. People are working on ease of process transferability, so to reduce the dependency on single systems. New material development, so which are currently not in the catalog of machine providers, but developing that non-catalog material which are of common use, working with either material manufacturer or machine manufacturer, increased end use production, innovative digital designs, automation and connectivity, hybrid manufacturing, process monitoring, lowering environmental footprint, and manufacturing centers for one-stop solution. And all of this leading to a more robust control and giving me good quality output at lower cost and lower time. And I think this is where I would stop and would like to take any questions you have.
Yeah, participants, please unmute and feel free to ask the questions. Yes, participants, please feel free to ask the questions to Dr. Vinaya. I
Either
think,
they have, I think uh, they have understood it all, or am I
okay.
making them sleepy?
Okay, anyway, but it was,
Ma'am, you explained very
yeah,
nicely, so we understood all the things.
yeah. Okay,
Yeah.
Just
participants, yeah, please go ahead.
so the different qualification process which we use at Eton, uh, what are they? Are the qualification by FEA testing or
So, it depends on the product, basically. It depends on the mainly driven by the customer requirement. So, some of the testing has to be done. So, it is governed by the customer requirement. But for example, if there are testing like in which environment that component would be, it may not be applicable to all, but sometimes you can say that if 4 part had sustained that particular environment, then it will also sustain in this environment. So some of the electrical applications you need UL certification or uh, fire retardancy V0. So if that material is certified with a 3 thickness or 2 thickness for V0, and if your part has that thickness, then you can always say that with the similarity or with the certification, we can go for the reduced testing for qualification. And some of them also can be done by analysis or similarity. So it depends
okay?
on what
So
kind of testing and what customer demand is.
okay, one more question on that one. So some suppose there is one part already qualified, which is manufactured by AM.
Hmm.
Can you use that for different configuration with the in same for qualification by similarity?
It as I said, it again depends on whether it covers my entire spectrum of range. So normally what you would do
Mhm.
a small, medium and largest part, just to give you an
Okay,
example, and then you can do for instead of 5 parts, you might go for 2 part testing. So it will reduce your effort. And
okay,
for environment, you can sometimes go for similarity, yes. But if it is like performance testing, right? If it is related to proof or burst pressure or flow or some thermal behavior, then sometimes you have to go for testing as guided by the customer.
okay.
Yeah.
And the PPAP for conventional and PPAP for additive manufacturing part, is there any difference or extra measure we have to take with respect to the AM processes?
It depends on. Okay, so it is very interesting question. So it also depends on how many parts you are printing. So you might land up checking every other part if the parts are really less in volume. But you can also depend on how many samples you are printing. So that's one
Mhm.
part. You also define key characteristics of the parts that would be tested in production environment. So once you do the developmental testing and planning, depending on the because it may not be possible to test every other. So you actually define what is your key characteristic. If those are fine on my final production parts, my part is fine, and those would be tested.
Okay. Thank you.
Okay, participants, any other questions? Okay, Dr. Vinay, I would like to ask, like you mentioned in your summary and the trends, like manufacturing centers were one-stop solutions. So
Hmm.
I think this is uh, not only for like additive manufacturing as a solution, one-stop solution, but this is in context with converging manufacturing trend, right? Can you elaborate on that?
So a one-stop solution is something where which makes your value stream map easy and faster. So there is less handling, less travel of part, where there is consistency is maintained. When there is too much of travel, uh, then it would be difficult. So manufacturing center, if I have one stop solution which would print, post process, and do other things, even the testing uh, uh, of each build, there are certain things which one needs to be tested. So even the material solutions, right? So it is the overall solutions that would uh, help me faster solutions, easy, better and easy tracking, and reduce times.
Yeah, I mean to say like many manufacturing techniques you are bringing at one station. Let's like the people call it as a converging manufacturing,
Convergent.
convergent manufacturing,
Correct.
like that. Okay. Okay. Thank you. So thank you, Dr. Vinaya, for very informative session, and also you focus like how it should, how it will go in the future, and how we should be equipped with. So thank you very much, Dr. Vinaya. Thank you for with us in this AICT ATAL FTP. So I thank you very much. I extend thanks from all the participants, and importantly, the AICT ATAL program or this initiative, which brings all of us together. Thank you very much.
Thank you, Professor, and thank you, participants. Have a great day. Bye.
So note for the participants, we will start the next session at 5 p.m. So stay tuned. We have a few minutes to go for the 5, so we'll start at 5. Thank you. So we'll have some short break and we'll start at 5. Thank you.